Howdy friends, it's Ben again. This is another video for Calc 3. This time we're taking a look at how you go about doing your integration in polar coordinates / cylindrical coordinates. A fair little bit of this will be stuff where we're looking at integrals across regions in 2 dimensions, because that's really the main change when you shift from rectangular to polar / cylindrical. Okay. All right, let me bring up my examples here. Yay, all right. Oof, okay, there for a second, I thought it wasn't gonna work. All right, so integration in cylindrical coordinates. So the main big change here is going to be this one right here. We are talking about dA. So the expression that we use for dA in this is going to actually be derived geometrically here. And all it's really asking us to do is to figure out what the, get the wrong thing there, what the area of one of these basic volume elements is. So what we have to do is to think about, if we take and change our R value by just a little bit, then we're thinking about going from one radius to another, or going from R to R plus dr. So that gets us a little bitty sort of annulus of a circle here. And when we talk about just changing the theta a little bit, then that means we are slicing out a little segment of that annulus. And so we are going from theta to theta plus this d theta. Now, if you do the algebra there, well, actually, I guess I should say first for the geometry, finding the area of a little section of a circle, you take 1/2 d theta times the area of the circle. Now, since we have between two circles, then we take the larger one minus the smaller one. So when you algebra that out here, you end up with a 2rdr, and then you also end up with a dr squared. Now, this is one of the little weirdnesses of calculus. Essentially, with that dr squared, since dr is going to be approaching 0, then we think about that as a higher order term. It goes to 0 faster than dr alone would. So that means we've got really just 2rdr times this 1/2 d theta, which multiplies out to say rdr d theta. Later on, when we talk about changing variables, we will see a different way to derive this that I feel a little bit better about, but geometrically, it's nice to be able to see this portion of it. Okay. All right, so we're going to do a quick example here, and the example is just asking us to take and evaluate this triple integral. But the triple integral that we're thinking about is going to be the triple integral that gives us the volume, the general volume for any cone, right? So what I did to set that up there was that I talked about the cone being z equals h times quantity 1 minus little r over big R, where big R is the radius of the circle down here, the base of the cone, okay? Now, the setup on that is that when you plug in r equals 0, then you'll get h, and when you plug in little r equals big R, then you'll get 0. And since it's a linear function, then we will just linearly, in a straight flat way, come down here from the apex of the cone down to the base, right? So our volume element, dv, is just going to be dz times the dA. So we're going to have this r dz dr d theta. Looks like a mess, but it's not hard to deal with, really. So as we're going along to evaluate that, the first thing to notice is there is nothing that depends on theta inside here. Since there's nothing that depends on theta, we can think about factoring this out and having the integral 0 to 2 pi d theta just be a separate integral there. Anytime you can completely factor out your functions on the integral, you can do that sort of thing. If you can't factor them out, if I said r plus z or r plus theta on stuff, I could not do the whole factoring out trick, right? So, as a matter of fact, I could have written this particular one much more compactly, and I just didn't think of it as I was doing that. So that if I wanted to here, I could think about the dz, since there's no z in there, just being this integral from 0 to h times 1 minus r over r. Yeah, no, I'm gonna just leave it the way it is. All right, I don't think I could actually make that work out as nicely as I thought. All right, anyway, since we're integrating dz and there's no z's, we just get a z evaluated from 0 to that. And when you plug in the 0, of course, you would get 0. So we're really just going to get that factor to appear down there, okay? And when we integrate d theta from 0 to 2 pi, we just get 2 pi. So just leave that hanging out to the front the whole time. And now with this part here, we're going to have an r in it. So it's probably easiest to go ahead and multiply that out. And then the other thing that I did was to say, hey, h is just a constant. It doesn't change. Kick it out to the front. So we're integrating r minus 1 over big R little r squared. Okay. So 1/2 little r squared, and then a 1/3 little r cubed. And of course, the big R is staying down there. So then when you plug in the 0 and the r, of course, the 0 stuff just gets you a minus 0. But we end up getting a 1/2 capital R squared minus 1/3 1 over r times capital R cubed, get some cancellation. And so this stuff becomes 1/2 minus 1/3 is 1/6. When you multiply that by the 2, that's where we get this 1/3 from. We've got the pi still hanging on. We've got the h still hanging on. And we've got the r squared coming in there. So your general formula for the volume of a cone is going to be 1/3 pi h r squared. I think we usually write r squared h, but yeah, either way. All right. So evaluation on these isn't really any different. It's really the setup that takes a little bit more thinking sometimes. All right. So this one here, we're asked to find the volume between these two things. That is clearly a sphere with a radius radical 6. And then this z equals x squared plus y squared. If you think of that as z equals r squared, and think in the zr plane, clearly a parabola, then if you rotate it, thinking about the theta, you get this paraboloid shape, okay? And I don't want to waste a bunch of time trying to figure out how to draw all this stuff on the computer. I can just give a rough draft here, or a rough sketch here. So we've got our sphere there, and we have this paraboloid here, and we can visualize that when the paraboloid hits the sphere here, it's got to be doing that kind of in a circle. And then we have to think about projecting that down onto the xy plane and figuring out our region of integration for that, okay? So this volume here, we mainly need to think about the intersection. And with that, we're going to take the x squared plus y squared plus z squared equals 6. And we're going to replace the x squared plus y squared with just a z, because we have the surface z equals x squared plus y squared. And that, of course, is something that we can factor nicely. And we know that the z is either a -2 or a +3. And from the graph, we know that we're talking about positive z values. So our z equals +3, and since it's z equals 3 and z equals x squared plus y squared, or z equals r squared, then the r needs to be equal to radical 3 for this region we're talking about. Okay. Now, the other bit of the description that I totally failed to read out loud to y'all was that we wanted to restrict this to having x being greater than or equal to 0. That means in the circle, we're just taking the right half. Okay. So we're going to set up our integral. And the top limit of integration, you've got to solve for z in the sphere. So that's where you get the square root of 6 minus r squared. And then the bottom limit of integration is going to be that paraboloid. And so you just have minus the r squared. And of course, dA is r d theta. Okay. So now we have to figure out setting up the integration. And so we think about starting at the origin and drawing an arrow out. That is the direction that r increases, going out from the origin. So it enters the region at r equals 0, and it exits the region at r equals radical 3, and that sets up our dr. And then the d theta is just this range here from 0 to, or this range in here on the right half. And I went ahead and just set it up to be minus pi over 2 to pi over 2. If you would prefer to do it with some other range, you can certainly do that, but yeah, that's probably the easiest. Okay. Now notice all that stuff is just functions of r. That means we can factor out the d theta. We are integrating d theta with from minus pi over 2 to pi over 2. That means we just get pi out of it. Okay. And then the hard part is actually integrating this deal here. But 6 minus r squared to the 1/2 power, we can let u be 6 minus r squared. The du would be 2r dr. So that's the reason why we get the 1/2 here. Since the new power of the u stuff is 3/2, that's why we get the 2/3 there. And of course, I totally neglected to notice the negative there, which is why there's a negative coming out front. Okay. And then integrating r cubed, I certainly hope you can do that in your head. All right. Once we get to this stage here, we'll cancel out some 2's, but otherwise it's plugging in the square root of 3 here, and then plugging in the 0 here. And when we do all that, we end up simplifying it as best we can, and end up with pi times 2 root 6 minus root 3, and then minus 81 over 4. I totally didn't do, all the arithmetic stuff there that I could have been doing, but I didn't figure you really wanted to watch that. So, all right, let's look at another bit here. Oh yes, this is, I don't think I should say it's the most important result from Calc 3, but it is one of the most important results for statistics, or for probability and statistics stuff, that we get the tools to do right now. Okay, so this function here is has a graph that looks somewhat like that. That's not a very good picture of it, but that graph is tied to a normal distribution. Once we know how to integrate this from minus infinity to infinity, then knowing that we get square root of pi out of it is going to actually tell us how to set up the normal distribution so that it will have the right kind of shape, and so that it will have an area under it turning out to be 1. Okay, so it's a trick. That's the main thing here, is there's a trick to all this. So if you took this integral we're trying to find, you cannot just integrate that. You can approximate it. You could get the power series for e to the minus x squared and then do as many terms of it as you want. But to get an exact value, we have to think about, if you took it and squared it, that would mean that we had this integral being multiplied by itself. And I went ahead and said, let's change one of them into y's. And then if we're doing that, we can just do the reverse of what we did with the d thetas a minute ago and have e to the minus x squared times e to the minus y squared, which simplifies as e to the minus quantity x squared plus y squared. And that is clearly r squared, okay? And when we swap out our dA from dy dx to the dr d theta, we pick up an r. Remember a minute ago when we did that u substitution and it involved an r? Exactly the same thing as this, all right? So we're going to integrate e to the minus r squared r dr d theta, but notice that there are no thetas, so we can factor the d theta part out there and just have 2 pi showing up. And then here we'll do a u sub. The u is going to be the minus r squared, so the dr would be minus 2r dr. So that means that we end up picking up a 1/2 there. And I'm seeing as I'm writing here that I did not write my minus 1/2 on that, but it should have been there. And then there's another just little typo thing here that I should have then written that when we plug in the infinity, we'll get 0 minus a negative. And when we plug in the 0, we get 1, noting, of course, that the 2 and the 1/2 have canceled out there. So that means that the square of this thing that we were trying to calculate is pi. So the thing we want is the square root of pi. Woot! Okay. So again, this figures into how normal distributions are set up. And it's something that we really we can't do with rectangular coordinates. So, all right, one more thing. I think this is the last thing anyway. Let me check about that. Well, yeah. So I need you to recall something from Calc 1. We had a formula where we said, if you want the average of a function over over an interval, that you would take 1 over b minus a and then integrate the function there. If that doesn't entirely make sense to you, what you need to think about is that f of x dx is taking little bitty segments, little rectangles, and it's adding them up. So the integration is really an addition tool. And then you're dividing by the length of the interval. It's really an average formula. It's just an average that involves an infinite sum. And it hides all of the infinite sum stuff that you wouldn't want to deal with from Calc 2 and the beginning of this course. So, well, if you can take 1 over a length and multiply that by an area in order to get an average function value, then if our function has a domain that's 2-dimensional, an f of x, y, then we ought to be able to find a volume by doing a double integral and then dividing by the area of the base that you had on this volume. And we should get an average then for that. So I did just a super quick sketch here that maybe you've got some sort of a volume and you want to get an average height on it, you know? And so you just integrate across that base of just whatever the z coordinate is. And the z coordinate, of course, is going to be given to you by whatever that upper surface is, f of x, y, okay? Similarly, if we go a step further, if we're doing something 3-dimensional, then you could get the average of that function that has 3 variables in it by taking a summation across some volume here and then dividing by the value of that volume. Okay, same as you divide by the value of the area here. All right. So when we're finding, in this example here, we're going to find the average value of our f of x, y, z, f of x, y, z. Why did I say it? Oh, yeah, f of x, y, z. Okay. It's going to be just x squared plus y squared. All right. Now x squared plus y squared, of course, since we're doing things in cylindrical, is going to just be r squared. So that will end up being a little bit nicer as we go along here. But the region is going to be in the first octant. So x, y, and z, we all need to be positive. And with our z being less than or equal to this 4 minus, what the heck? Change it to polar. 4 minus 2r, right? You say 4 minus 2r, and that's a z equals 4 minus 2r. Think of it as being a straight line that has a negative slope. And then you would get, you would, it's easier to draw than to say, you would get a line like so. Once you've got that line, then you think about rotating it around the z-axis and giving it all the possible theta values. And that is when we see that we've got a cone out of it. So we're, I made a little bit of an error here that I'll have to fix as I go, but we're going to know that the volume of a cone is given to us by this formula here, 1/3 pi h times r squared. So we would get 16 pi over 3, but we don't have the whole thing, do we? What we have instead is 1/4 of a cone. And so I should say 1/4 of a cone. And so I'll put the times 1/4 out at the end here, and we'll have 4 pi over 3 for our volume. Okay. So that's going to be the thing we divide by at the end, this 4 pi over 3. Then we're going to set up our integral here. And since the function we're averaging, we said was going to be just r squared, then we put the r squared there. And then the r dr d theta comes in because of the dv, okay? So the r dr d theta there is our volume element. So we need to think about, with this cone, we are integrating and having an arrow going up and hitting z equals 0, and then hitting z equals 4 minus 2r before it exits the region. And so our limits of integration with the z are 0 and 4 minus 2r. Then for the region in the plane, since we're only getting 1/4 of this cone, we will say I need to start at the origin and go outward. I encounter the region at r equals 0, and I exit it at r equals, what was it, 2? So that gets me the limits of the 0 and 2 for my r's, right? And there was another copying error there. I forgot to put my dz on the previous one. Okay. So, wow. I'm sorry, folks. This is just littered with little typos that I'm correcting as we go along. So when we integrate with respect to z, we will get a z there. It goes from 0 to 4 minus 2r. We have the r cubed hanging on there. And so we end up with r cubed times the 4 minus 2r in there. Now, the theta did not appear in here, so we can just pull it out and have the pi over 2 hanging to the front as a constant. And now we just have a single integral to do, and it's just a polynomial. So multiply it out there, you'd have 4r cubed. When you integrate that, you get r to the 4th. And then you'd have minus 2r to the 4th. When you integrate that, you get minus 2/5 r to the 5th. We need to plug in the 0 and the 2. So we end up with 16 minus 2/5 of the 32. And that should calculate out to 8 pi over 5. And so finally here, the average that you get should be that integral divided by that volume. And then you can cancel out a little bit of it and end up with 6/5. And I should probably take and lasso that piece and move it down a little bit. Oh no, I didn't lasso my pie. Okay, there we go. All right. And so that gets us our examples that we want to take a look at on there. So your setup on this basically is, the new thing is figuring out how to do the integration where you go out from the origin to wherever you're going out to. It can be something fairly complicated, but in general, in polar coordinates, we want to be integrating over circles. If you're integrating over rectangles or trapezoids or triangles or something, probably you're going to do that in rectangular coordinates. Okay. But for stuff that is circular, cylindrical coordinates often makes it easier, if not actually making it possible when it was impossible before. So, all right, I'm going to go ahead and stop there and look at the homework, ask questions as you need to, and I'll see you next time.